We are the Ski Boot Flex testing rig group, aka the coolest kids. So this is our background section. Key question of our project is, can we build a fixture to flex ski boots that can be used by brands to standardize the stiffness value of boots being sold? And a little bit about why we chose this. One of our group members, Sam, found himself breaking ski boots of the same stiffness, while another pair with the same stiffness being like perfect for him. He was frustrated because they're expensive and he spent a lot of money on boots. So it inspired us to build a rig that, in junction with a load frame, can test ski boots and help calculate more like universal values. Some prior work that's been done was the Atomic Ski Boot Flex Testing Machine, which is a ski boot company. And the article written by Wild Snow just kind of goes into the boot testing thing that they have in their facility. They have a similar setup, but they did a lot of repeat like fatigue testing on the boots, while our setup really is not meant for that. We use a static load frame for our test. This matters because it has social and economic impacts. The ability to standardize the stiffness decreases frustration of consumers and prevents unneeded boot damage. Inaccurately labeled boots in use in the wrong setting can be damaged due to misrepresented stiffness, and the economic benefit is a problem that Sam himself knows after buying like 3 pairs of boots in like a month. A relevant model would be a strain curve, as you can see in the photo to the right.
As for our method, based on the previously performed study, we assigned an ideal range of motion under kind of a standard skiing load to be approximately 15 degrees forward from the standard lean of the boot, based on a presumed kind of shin length from the hinge of the boot of 25 centimeters. It leaves us with a displacement of approximately 6 centimeters at the location of the applied load. Based on our goal of testing boots to failure, we hoped to find a way to apply a displacement double that of at least 12 centimeters. The third quartile in previous tests for the stiffest set of boots required approximately 1,000 newtons to be flexed through the proper range of motion. We intend to use a load frame with at least that, but hopefully at least 2,500 newtons to achieve the intended range of motion. We ended up using a load frame with 100,000 newtons because it's what we had available and it worked great. As for kind of the prosthetic to apply the force to the boot, we used a 3D printed model of a shin and foot in conjunction with a hinged metal frame. The printed portion was printed with a very high infill to maximize strength, and the internal frame was designed to distribute the load as much as possible without creating unnecessary sources of error. The model shown here is the CAD design of the rig that we designed. It uses 2 linear bearings to constrain the force to be only axial, ensuring that we don't damage the load frame in any way. And that rig is attached using machined parts from Jacob Weller and the CAD models. These attachments can be found on the next slide. These are said CAD models of the parts that we use to attach the frame or the jig to the frame. The experimental conditions in the project were all implemented in the design of our rig and attachments. Attachments were designed and machined so that we could fit our specific rig into the frame. Linear bearings were added to ensure no damage was done to the load frame by off-axis loads, and force was being applied through the load frame consistently so that we could ensure consistency and repeatability through different tests. And a flowchart of our project can be seen below. Our design of experiment table can be found below as well. These values were found through testing, and they're not included in the methods section. Force and displacement values are directly received through boot testing, and stiffness values are then calculated. For our variables, we had the applied force and the displacement of the boot. Controls, we had testing boots designed for a similar function and using the same testing rig for each boot. Our parameters were that the force applied to each boot could be easily held constant or varied to test its effect on the boot deflection. Measurement techniques were just using the measurement capacity of the load frame and its readings for extension and load. And our test equipment was the Composite Labs static load frame, 80/20 structural aluminum and attachment brackets, various screws, bolts, machined aluminum stock to attach the jig to the uh, load frame, and 3D printed designs in PLA. The standards we used, the load frame was recently calibrated and all procedures were done to the following standards in the manual. For our budget, our ski boots for testing were donated. The bracket hardware to hold the boot was provided from the machine shop. The load cell and load frame were provided by the school. Any of the 80/20 extrusion and machined aluminum stock were from the makers or from the machine shop stock that they had. The 6-inch linear bearing was $75 from McMaster Carr, and the 3D printed PLA was from the Makerspace. If we had to purchase everything that we used, barring what we had, because it ended up that most of our materials were supplied, our cost would have been about $900 just for the jig. And then depending on what boots we decided to test, it would have been another $500 to $1,000 to test the boots. Our process for the actual testing involved familiarizing ourselves with the load frame and program, fitting the attachments and ski boots into the load frame, securing all the joints, setting preventative safety measures like putting up the sheet of plexiglass and ensuring we were all wearing safety glasses and proper protective equipment. We did our first round of testing with applying the force and collecting data, and then did the same steps for all of our subsequent testing, and then we removed it from the load frame. This is an image of our Gantt chart throughout the project. The potential risk of this project is due to high amounts of potential energy. With the constant force being put into the ski boot, there is a low risk of the boot actually breaking and plastic coming off of it. It's low because the likelihood of it occurring is low and the severity of injury, if it occurs, is medium. But the best way to minimize this risk and what we implemented was to decrease the likelihood and the severity. The likelihood was decreased by only putting a certain amount of force on, which we limited. And in order to get a larger range of data, our group will break 2 to 3 boots to determine this optimal constant force. To decrease the risk of actually breaking a boot, the severity of injury can be decreased by wearing safety glasses during testing and putting up the sheet of plexiglass in front of the actual load frame. But to prepare for emergencies, group members not applying force or measuring deflection stood far back, prepared to call emergency services or get help if needed.
So for our results section, we used an extensive spreadsheet to analyze our data from the load frame, which was both the displacement, time, and also the load applied. And this helped us calculate the repeatability. The data set was extremely large. We were looking at about 35 to 4,500 points of data for each test. So we needed the spreadsheet to analyze all of that. We used a Blond-Altman analysis to determine the overall repeatability of the experiment, as well as how it changed at higher loads. This is because at low loads, like let's say you're just standing on the boot, there's not a lot of force being applied. Maybe the mechanisms in the boot that give it its stiffness aren't actually engaged. So by separating it, looking at just the higher loads, we're able to get a better gauge of what the stiffness of the boot looks like when it's fully engaged. We only analyzed the second boot with the Blond-Altman analysis because the first one yielded inconsistent results. We believe this to because the very first test that we did, we had the firmness setting on the boot was loose, and there was also unnecessary contact between some of the parts in our rig that created friction. And these errors were fixed in the subsequent tests, and the figure on the next page shows that we had better consistency amongst these boots. So this is all 4 of our tests on a load versus extension graph. And the blue line is the very first test that we did. And you can see that it is a lot more inconsistent compared to the other three. When we fixed the errors we had in the first test, we had the red line, which is the second test of the first boot. As you can see, it is a lot more in line with the test we had for the second boot as well. So we decided to just look at the second boot because we believed that because the second test of the first boot was more consistent, that the repeatability would be the same for either the left or the right boot that you were testing. So the Bland-Altman analysis uses a term called limits of agreement, or LOA. These are measured using the mean and standard deviation. The formula is there for a 90% confidence interval, the upper range being plus and the lower range being minus. The total LOA range can be found using these upper and lower limits with respect to the calculated mean. And essentially, this represents the acceptable load variance for tests to be considered repeatable. And when put into a percentage with the maximum load for that test, the direct repeatability can be analyzed. Essentially, the way Bland-Altman works is that if the percentage is below 5%, then it has excellent repeatability. If it's 5 to 10%, then it's moderate. And if it's above 10%, then it's poor repeatability. So when we look at the boot 2 tests for the entire load range, we have a maximum load of about 550 newtons, and the LOA of max load was found to be just under 7%. So this places it in the moderate range, slightly closer to the below 5% that we're looking for. And even though this isn't the optimal repeatability, it doesn't represent the full analysis of the boot. As stated earlier, the lower loads don't have all the engaged stiffness mechanisms of the boot, so the material properties are different. So this means that at those lower loads, the repeatability can be misrepresentative of the boot itself. So what we did is we separated into 3 load ranges, 0 to 200 newtons, which just represents the kind of neutral state, not very engaged. And 200 to 400 newtons, which kind of represents that in-between zone. And then the 400 to 550 newton range is the highly engaged. And as we can see, the percent of maximum load significantly decreases as we increase with the load ranges. And this is very promising, even though it's a little higher than the overall load range that the percentage that we were looking at before at about 7.3%. We did not test these boots all the way to failure. So essentially, with this data, we know that as we increase the load, as the boot is more engaged and the repeatability becomes more important, the repeatability actually gets significantly better. So this was very great to see. It shows that our load frame did work as intended. And as we follow this trend, the repeatability will only increase. So while we did have an error analysis, so while the linear load bearings provided minimal shear on the load frame, it is possible that there were loose fittings that could have impacted the results. Additionally, frictions in the pin on the roller could have misrepresented the force being applied onto the boot. With these problems fixed, the group does expect the results to actually show better repeatability. So given that the current data already shows moderate repeatability, it's a clear indication that the proposed test rig can provide significant repeatability for ski boot flex measurements. And this is the right photo shows the firmness setting that I was talking about earlier, and the clips on the left are also some of the engagement mechanisms that I was talking about. At lower loads, these aren't fully engaged. They're just kind of holding your shin in the boot. So once you reach higher loads, there's more tension on those and they become engaged.
So the objective of this project was to assess the stiffness of ski boots by quantifying the force required to produce a given displacement using custom-built test rigs and load frame. 2 ski boots were tested to evaluate the mechanical repeatability and stiffness consistency. Analysis included load extension, curves, pair t-test, and Bald-Altman comparison. Our test successfully and the setup proved to be reliable in capturing the force displacement behavior. Using the Bald-Altman analysis method, our results showed that the mean difference was approximately 3.86 newtons, which when using the Bald-Altman's method, the closer you are to zero indicates minimal bias between tests, which means that our test setup is consistent and repeatable. Despite identical nominal flex ratings, the 2 boots display differences in stiffness characteristics. All test sets exhibited an increase in load with time and extension consistent with the elastic mechanical response. Assumptions: the environment was assumed to be stable and the room temperature similar with humidity to ensure consistent test setup. The team expected that the boots might follow a linear elastic model for small deformations. Boot settings, boot seating and alignments inconsistencies such as minor deviations in mounting or synthetic leg positioning could have altered the loading profile. Manual resets between trials may have introduced variability as the remounting of the boots or residual deformation from prior tests might have not been uniform, leading to inconsistencies across trials. Material variability was also a key concern because real-world differences in wear history, internal padding, compressions can affect the stiffness of the boots. Inconsistency. So in conclusion, inconsistency between nominal flex ratings and measured stiffness can confuse customers when choosing boots. Standardized mechanical testing could offer more reliable information to help purchasing decisions. For manufacturers, providing consistent and quantitative stiffness data would promote transparency and reduce return rates caused by fit flex issues. For future plans, we plan to expand the data sets by including more boots for different brands, performing 5 to 10 trial per boots for better statistical validation. We will refine the test fixture by using more anatomically accurate synthetic legs and ski binding interface. We also aim to draft and share a standard testing protocol for industry feedback. To enhance data quality, we will improve repeatability through better mounting guides and noise filtering. Field validation will be conducted by collaborating with boot fitters or ski resorts, and the public-facing website will be developed to display test stiffness data, helping consumers make informed decisions. Sources and acknowledgements. We would like to acknowledge the Clarkson Makerspace, Carl Hoover, Jacob Willer, Madi, and also all members of the MAE department.
Thank you.
Okay.